Hello everyone, in this video we are going to continue our discussion about the graph algorithms and we focus on depth first. So in the previous video we have discussed about the graphs and this fact that many problems in computer science can be modeled using graphs. So in a graph you have a set of nodes and you have some connections, some edges between the nodes. In many problems, we need to visit the nodes in the graph. So we need a kind of traversal algorithm. We have two main graph traversal algorithm that visit the nodes based on, the breadth first order or depth first order. In the previous video, we discussed the breadth first order. In this video, we are going to talk about the depth first graph traversal. So let me give you a use case for the DFS. Assume I'm actually designing a video game and you are searching, for example, at some point in a maze, we are looking for a path to the exit point. For example, assume that you are at a point like here, you want to find a path to the exit point, this green point here. So I can model the problem as a graph problem. You can just think about each block as in the maze as a node, and there is a path from each block to its adjacent block if there is an edge from each block to its adjacent blocks, up, left, right, and down. If the color of them, both of them are white. So for example, from this block, you can actually move to this block, right? Because this is white, but you cannot move to up or to left because they are black, the pixels are black. So basically we wanted to find a path from this point. So basically you go to this block, then you go to this block. You can divide your maze to different blocks, right? You go to this block, you go to this block, and until you actually find a path to the exit. Okay, how can I solve this problem? Remember, we talked about the breadth first. So the breadth first can solve the problem for me. It can find the path from if you run the breadth first over this graph, if you model the problem as a graph, and if you run the BFS gives you an answer. And the good thing about the BFS is that it gives you the shortest path from this point to the exit point. That's really good. But the issue is that here I don't really care about the shortest path. I just wanted to find any path. It doesn't matter even if it actually takes too long. The length of the path is too long, but I wanted to find the path as soon as possible. The properties of the breadth first search was that it visits all the adjacent nodes, all the neighbors at the distance 1, then visit all the neighbors at distance 2, then visit all the neighbors at distance 3. So they visit the nodes in a breadth first order. If you run the BFS, it solves the problem. It gives you a path. It gives you the shortest path. But in cases like this problem, I don't care about the shortest path. I just want a path as soon as possible. So running BFS is not very efficient. I want to find a path. I don't care about the length of the path. I just want to find it as soon as possible. This is exactly where depth first traversal of the tree comes handy. So what is the idea of the depth first? Unlike in BFS that you start from a node and you visit all the neighbors first, then you visit the nodes in the second level. In the DFS, you start from one node and just visit one of the neighbors. Okay, visit one of the neighbors and immediately just move to that neighbor, and from there again visit a neighbor of that one that you haven't visited that. So if I am going to simulate that, this is going to look like this. Again, assume you started from node 1 if you run a DFS, you just visit one neighbor. Let's just assume that we don't care about any order, just randomly choose one of the neighbors. From 1 you can visit 2 or 3. Let's just assume we visit 2. So from 1 you go to 2, and in 2 you just move, look at all the neighbors, just take one of the neighbors which hasn't been visited. So you can take one, let's just assume that we take 4. So from 2 you go to 4. Okay, you see that from 1 I went to 2, and from 2 I went to 4. I didn't actually visit 3 or 5 yet. I just moved to 4. That's why, I mean, this is depth first. You just go deep in one way, instead of visiting the nodes level by level in breadth first order. You visit them in depth first. You just go deeply in one way, and you just continue until you visit all the nodes that you can visit. So from the node 4, I can continue, take a neighbor that you hasn't visited. So you only have 2 neighbors, 2 and 5. 2 have been visited, so you can't take that 2. Let's just take 5. You go to 5. From 5 you can either visit 3 or 6. The other 2 neighbors, you have visited them, so you can't go there. So let's just assume you go to 6. You go to 6, and from 6 there is no other neighbor that you haven't visited, right? So the idea of depth first search is completely recursive idea. It's just like when you reach to 6, if there is no more node to visit, you go back to your parent. It's just like if you think of it as a recursive call, from 5 you call the recursively over your child, for example, one of your neighbor, like 6. You go to 6. In 6 there is no other function call. You can't call anything else. So the function call will terminate, and you automatically go back to the parent function call, which was 5. And in 5 again you just scan, and if there is any other neighbor that hasn't been visited before, you go there. So from 5 you can go to 3. In 3 you have 5 neighbors, but 2 of them have been visited. 3 of them have been visited, 1, 2 and 5. So you can go to, for example, 7. So the function call goes to 7. In 7 you have a neighbor that hasn't been visited, you go there. You go to 8. In 8 you don't have any neighbor that hasn't been visited, right? So it's just like the function call will go back. From 8 you go back to 7. In 7 there is no more neighbor that hasn't been visited, so from 7 you go back to 3. Again in 3, is there any neighbor that you haven't visited? No, there is nothing remains, so you go back to 5. And it's just like this. From 5 you go back to 4. From 4 you go back to 2. From 2 you go back to 1, and you are done. Okay, so this is the idea, and it is clearly a recursive idea, although we can implement an iterative version of that as well. I'm going to show you the iterative version, but let's just actually look at the recursive version of that. Very intuitive. Again, I have the input of the DFS is going to be a graph, a set of vertices and a set of edges of that, and a node, a starting point that you run the DFS starting from the node S, one of the nodes in V. So just to make sure that I'm not going to visit any node twice, very similar to the BFS, we create a Boolean array. We call it visited. We initialize for all of the nodes to be false. For the very first node, that's the starting point, we change it to true. And then we call this recursive function, this recursive method, which call it explore. Okay, now let's see that what does the recursive method do. For any node u, the argument of your recursive function, you just need to look at the neighbors. If for any of the neighbors which hasn't been visited. If it is visited, you are not going to actually go back and visit that, right? So if the visited is false, what you do is that you visit it. So basically you change the visit for V to true, because you don't want to actually visit it again, and you recursively run the explore over V. And that's it. That's the whole recursive definition for the U. Now you can see that when you actually come back from this recursive call, you might have visited many other nodes which are the neighbor of U. So depending on if you have visited everything or not, you may just finish this loop as well and actually get out. Let me actually show you that how we run this over the previous graph that we had. I'm going to just show it to you over a couple of steps. 1, 2, 3. I think it looks like this. 4, 5, 6. There was a connection here. 7 and 8. Let me see if I'm missing anything. No, apparently I got everything. Okay, so let me use a different color. You start from the node 1, so S is 1. So it's just like the function call. You call the explore over 1 and it is visited. So I'm going to just show the current function call is over 1, and we mark everything that has been visited using blue. So you are here. Then, okay, so U is going to be, this is just like you have a function call. Let me write the function call somewhere else here. The function calls, okay. Explore over 1. Okay, over 1, you call a function call over, okay, go over all the neighbors of U. So it doesn't matter which order. Let's just actually follow the order that we have visited them before. So the first one is 2. Okay. Is the visited 2 false or true? This is false, right? So 2 hasn't been visited. You just change it to true. So I'm going to actually change the color of that node to blue. And then you call the explore over 2. So in your function calls, you call the explore over 2. So let me actually just, because it takes too much space, let's just show it using just E. Okay, now the function call is at 2. In 2, U is 2. Right? You look at all the neighbors of 2. Okay, one by one. Let's just assume that the first node that you visit is 4. The you check is 4. 4 hasn't been visited. It is false for it. So you change and make the visit true, and you call the explore over 4. So you call the explore over 4. You are now at the node 4. You see that exactly the way that you are visiting the nodes is just showing you this set of the function calls that you call. And from 4, the only neighbors that you have is 4, 2, and 5. 2, you can see that 2 is the visit of 2 is true. So you don't go back to 2. The other neighbor is 5. It is the visit for that is false. So you change it to true and you call the function call E for 5. Okay, now the function call is at 5. At 5, let's just check all the neighbors. For example, the first one is 6. 6 hasn't been visited, so you change it to true and you call the function call over, let me just draw it here, E over 6. okay? Then your function call is at 6. So you are at 6. The only neighbor that you have is 5. The visit of 5 is already true, so you can't go to this if statement, and you are done. There is no more neighbor, so the function call of 6 will finish and it goes back to the function call of 5. This is exactly what happened in the let me actually just mark all of these edges. So you actually go this way, and from 6 you go back to 5, right? Your function call goes back to 5. In 5 there is one more neighbor, 3, that hasn't been visited. The visit for that is false, so you call the function call over 3. Okay, so from 5 you visit 3. In 3 you can visit, for example, 7, so you call your recursively call the same function over 7. In 7 you call it over 8. In 8 there is no neighbor, there is no other function call that you can actually call, so this loop will terminate. You can't call anything else, so it's just like from 8 your function calls are going to back. This is exactly what happened over the graph. From 7 you go back to 3, from 7 you go back to 3, from 3 you go back to 5, from 5 you go back to the function call for 4, from 4 you go back to 2, and from 2 you go back to 1. So it's just like when you are done with 1, you just go back and you have visited all the nodes. Okay, this is a recursive idea, and in fact this graph that I just showed you, this let me use a different color. This graph of the function calls is exactly the which looks like a tree. You can see that this is like a tree. This is going to be exactly similar to the idea of a tree that you created using BFS. You know, see that if we visit the nodes in a depth first order, we also get a tree, but the tree looks completely different than the tree that you get over using the BFS. Okay, so I'm going to come back to the idea of the DFS tree and the different properties that we have for that. So let's just actually continue. What is the time complexity of this recursive algorithm? It is not as easy as analyzing the time complexity in the case of the BFS, because BFS was iterative, it was much easier. But we can analyze the time complexity here by just thinking about this idea. Okay, I have a recursive function. What I need to calculate is how many function calls in total I would have, and what is the cost of each call. So what is the cost of each function call? The cost of each function call will depend on this loop. This loop basically tells me that whatever is the argument that you see that we just have different actually arguments. All the arguments of this function calls are going to be some node. What is going to be the cost of each function call? The cost for any node u is going to be the degree of the node u. Okay, so you check all the neighbors of u. You check all the neighbors of u. But how many function calls I would have? This actually picture is going to make it easy. You see that you call the function call over all the nodes. You have exactly one function call for each of the nodes, and exactly one, not more than that. Okay, so in total, if I have n number of nodes, the number of function calls is going to be equal to n. The cost of each function call is the degree of each node for every function call. So I need to just get the summation over all of this. So this is going to be the summation of all the degrees of the nodes. you can see that this is exactly the time complexity of the BFS, right? And the time complexity in total, we will write it as O of n plus m, in case that m is smaller than the number of vertices. You keep both of, usually m is greater, but if the graph is so sparse, the n can be actually larger, so that's why we keep both term here. O of n plus m is going to be the time complexity of DFS, very similar to what we discussed for BFS. There is the very first property of the DFS algorithm is that if your graph is connected, at the end, if it doesn't matter which node you start, from that node you will visit all the nodes which are connected to this node. If there is a path from you to any node in the graph, all of those nodes will be visited at the end. When you run the DFS once over U, it will cover all the nodes which are connected to this node. Okay, this was exactly the same property that we discussed for BFS. Remember when we talked about the problem of finding, checking that if the graph is connected, or if for example, finding different connected components of the graph that we solved it using BFS, you can, instead of BFS, you can run DFS. In terms of this property, DFS and BFS are very similar. You can either use DFS for finding all the connected components, or you can use DFS. Both of them will work if you have undirected graph, and the time complexity of both algorithms is the same. Both of them will solve the problem for you. So the proof of this, I'm going to just leave it. It is very similar to the proof for the BFS. If the graph is too large, in any actually problem, if your problem, the size of your problem is too big, and the number of recursive calls is going to be too much, so you may get an issue if you write your problem in recursive way. So that's why always it is better to write your algorithm in iterative version. If you can write something in recursive version, you can definitely change it to the iterative version, right? So for the case of DFS, also, if we have a very large graph, we might actually end up to an issue, because if I keep all of the recursive calls in the memory, I will run out of the memory. I will get some stack overflow issue. So we can write an iterative version of the DFS. A nice thing about the iterative version is that this is going to be quite similar to what we wrote. In terms of just the algorithm, the written algorithm, it is going to be very similar to what we did in the case of the BFS. The only difference is that instead of using a queue, we are going to use a stack. If you compare this algorithm with the BFS algorithm, they actually looks exactly similar. Let me actually show you this. For the algorithm for BFS. Okay, this is the algorithm for BFS. Remember, we just created a queue, and in a while loop until the push the starting point to the queue, and while the queue is not empty, you just remove something from the queue and visit all the nodes of that, push them to the queue. We are going to exactly follow the same pattern for the case of the DFS. Instead of a queue, I'm using a stack. And nicely, just changing this structure from the queue to a stack, it completely changed the order of visiting the nodes. So queue will make sure that you visit the nodes in a breadth first order. A stack will make sure that you visit the nodes in a depth first order. So I created the empty stack. You push the starting point to the stack. You have a loop until the stack is not empty. You just pop something from the stack. You mark the visit for that true, and you visit all the, you actually go over all the neighbors of V. If it hasn't been visited, you push it to the, you push all of them to the stack. Okay, let me just run this iterative version. We have actually run the recursive version over that algorithm. Let's run the iterative version over the same algorithm so you get the idea. So let me see. I'm going to copy this and put it here. Okay, so makes it easier to actually run the DFS, this iterative version over the algorithm. So, okay, so you start from the node 1, right? So let me actually just write that stack, shape of the stack for you here. You push 1 to your stack, okay? It's just like you visit the node 1. Then, while a stack is not empty, you remove something, so 1 will be removed from the stack. So it is not in the top of the stack anymore. What you do in the loop is that you, for all the nodes in all the neighbors of u here is equal to 1. Okay, for all the neighbors, if you haven't visited, you push it to 3. So you push, for example, 3. You haven't visited 3, you push it to the stack. The other neighbor of 1 is 2. You haven't visited that, so you push it to the stack. Okay, so what happened here? There's no neighbor, no other neighbor for 1. You go back to the top of the stack. A stack is not empty. What you do is that you pop one more item from the stack. So the item that will be removed will be 2. Okay, so let's see that what would happen in this case. So for 2, how many neighbors it has? It has 4 neighbors. 1, 3, 4, and 5. Let me actually just put 4 and 5. Okay, so one thing that happened in the previous loop was that before we push the items to the stack, we marked them as visited. So 2 and 3, both of them has been actually already marked. Okay, but what happened over to 2 is going to actually check all its neighbors, 1, 3, 4, and 5. So 1 and 3, they are not, the visit for them is false, right? Sorry, the visit for them is true. You have already visited them, so you are not going to push them back in the stack. And you see that 3 is already in the stack. 1 was processed before. So what would happen? You will push 5 and you will push 4. Okay? So now when I'm done with this loop and go back to the beginning of the outer loop, the stack is not empty, and what you will pop here, you see that what you will pop is going to be 4, the top of the stack. Okay, the last item that you have pushed to the stack will be popped from the stack. That's why from 2 you are going to actually visit 4. You are not going to check 3. 3 is still in the stack. This is the way that the stack helps us to run a DFS, to execute a DFS, unlike a queue. If you had a queue, here the value that will be removed is going to be the front of the queue. So the BFS would actually go use a queue. It will remove this one, but the DFS would use a stack and it removes the top of the stack. Okay, so the last item that has been pushed will be visited now. Unlike the BFS, that the first item that, the item that has been waiting in the stack the longest is going to be visited first. Okay, so this is exactly the difference between the DFS and BFS, and how nicely queue and a stack is going to help us to execute these two algorithms. If you think about the idea, it is very nice. The main two algorithms over the graphs are going to BFS and DFS. Both of them are visiting the nodes, just in a completely different order. And the two main data structures that we have are going to be queue and stack. One of them is used in BFS, the other one used in DFS. Kind of it shows you that how, complicated the algorithms are related to each other. Algorithms and data structures and everything are related to each other. I think I found it very interesting the first time that I encountered this fact. Okay, let me actually just continue. That's running the DFS over the, running the iterative DFS here. So when you visit, okay, so you already actually for 2, you already put 4 and 5 in the stack. So at when you pop the 4, okay, when you popped 4, there is no other neighbor of 4 that hasn't been pushed to the stack. So you don't actually push anything in this loop. You go back to the top, you remove another thing from the top of the stack. So 5 will be removed. This time you will be 5. So at 5, you are going to visit all the, you are going to check all the neighbors, which they haven't been visited before. You didn't actually check them before. There's only 6. So 6 will be pushed to the stack, and you marked it in the visited as visited. Okay, so you go back to the top of the outer loop. So a stack hasn't been, a stack is not empty, there's still something in the stack. You remove the top of the stack, you pop. So U this time is going to be 6. 6 doesn't have any neighbor that hasn't been visited, right? So this loop won't push anything to the stack. You go to the top of the outer loop. The stack is not empty yet. You pop something. The value of U will be 3 this time. So at 3, you will check all the neighbors again that haven't been actually visited. So you push, for example, 8, and then you push 7. So these nodes are going to be marked as visited, and you go back to the top of the loop. The top of the loop will be, the top of the stack will be popped. 7. Again, 7 doesn't have any neighbor that hasn't been marked as visited. So you go back to the top of the loop. You pop something from the stack. So U is going to be 8. Again, for 8, there is no other node that hasn't been visited before. So you go back to the beginning of the loop. The stack is empty, right? The stack is empty. So the whole algorithm will stop. Now you can actually see that, analyzing the time complexity of this version is much easier. Each node will be pushed to the stack only once. And for each node, you will check all the neighbors in this loop. So the time complexity is going to be O of n plus m. So exactly similar to what we did for the BFS to create a tree, DFS algorithm is going to give me a tree as well. So to actually create the tree, the DFS tree, something that we actually discussed here. Remember I told you that the function calls actually gives me the tree. But basically I'm going to create take a set of edges, those edges that you visit during running the DFS. So I'm going to update the algorithm. I'm going to work on the recursive algorithm, but you can just do all these updates over the iterative version as well. There is no difference. I'm going to update the algorithm, extend it, and very similar to what we did for the BFS, I'm going to add an array, let's call it parent, that this is going to actually keep the edges for me, all the edges that we visit when we are running the DFS, which at the end, this set of edges are going to create a tree. So the array is called parent. We put null for the parent of the starting point because you start from this node, no one is going to come into this node, so the parent of S is going to be null. But later on, whenever from each node you are visiting another node, you are calling the function call over the node, you will keep the parent of that node to be you. So from you are visiting a neighbor V, right? The neighbor hasn't been visited before, so this is the first time that you are visiting V. Before calling the explore over, before calling the recursive call over V, I'm going to just store in parent V so that I know that the parent of V is you. Where I have called explore over V, I have called it from you. Basically, whenever you are done from this function call, you come back to the function call corresponding to you. This is going to create a tree for me. The proof that this is a tree is very similar to what we did for the BFS, so I'm going to actually leave that one as well. So here, these green edges are exactly showing that DFS tree. So you from 1 you visit 2, from 2 you go to 4, from 4 you go to 5, from 5 you go to 6. The function called go back, so basically the edge that we keep is just 5 to 6, and then from 5 there is an edge to 3. From 3 you visit 7, and from 7 you visit 8. Okay, so this is a tree, and this tree is completely different than the tree that the BFS gave you. If I'm going to show you that what was the tree of the BFS, the tree of the BFS would, let me, choose a different color. 1. Remember from in the BFS, the tree looked like this. It was a rooted tree. Look like this. Unlike your DFS tree that you can see that usually in the case of the BFS tree, we show it as a rooted tree because the BFS tree shows you the shortest path. Shortest path from 1 to other nodes. But when we are actually talking about the DFS tree, we usually show it as a a directed graph that basically just show you the the way that you deeply went down until you reach to some stopping point. So I need a couple of terms that I'm going to refer to them in the algorithms, in the rest of the problems or algorithms that we use the DFS in. So I'm going to define them. The first term is ancestor. If your tree, in your DFS tree, we will say that, okay, the node U is the ancestor of node V if you have visited U before V, and if there is a path in your DFS tree from U to V. So here, for example, 5 is the ancestor of 7. Why? Because you have visited 5 before 7. Because in the DFS tree, there is a path from 5 to 7. Or for example, 3 is the ancestor of 8 because you have visited 3 before 8. There is a path in the DFS tree starting from 3 to go to 8. 1 is the ancestor of all the nodes here because you started from 1 and there is a path in the DFS from 1 to all of the nodes. You visited 1 first. So 5 is the ancestor of all the nodes 6, 3, 7, and 8. Or you can actually here see that 6 is not the ancestor of 3 because there is no path in the DFS tree from 6 to 3. 5 is the ancestor of 3, but 6 is not the ancestor of 3. Basically, if you think about this tree, 6 is not the ancestor of any node. From 6, there is no path to other nodes in the DFS tree. So, like the ancestor, we can call we can define the descendant as well. So, if U is the ancestor of V, we say that V is the descendant of U. If there is a path from U to V, U is the ancestor of V, V is the descendant of U. So after defining the descendant and ancestor, the other term that I need and I can define is the back edge term. All those edges which are not a part of a DFS tree, those edges are a part of the original graph, but they are not a part of the DFS tree. We call it a back edge. For example, the edge from 5 to 2. So why we call, what is the idea of calling it a back edge? Basically, it is telling you that there is an edge from, 5 is the descendant of 2, right? It's just telling you that in the original graph, there is an edge from some descendant to some ancestor. It's just like although you are visiting 5 after 2, but when you reach to 5, you can actually go back to 2, right? It's just like you're looking back at your ancestors. That's the idea that why we call it back edge. This is just coming from this fact that we have a DFS tree. Some nodes are the ancestor of some other nodes. Some other nodes are the descendant of some nodes. And those descendant ancestors are just coming from the DFS tree. Okay, so all the edges which are not in the DFS tree, they are going to be some back edge because they are using them. It is just like from some descendant, you go back to some ancestor. There is a link from some descendant that go back to the ancestor. Now you can actually get this idea that probably this back edge is going to help me to find some cycle. We are going to talk about it later. One more thing that we will add to our algorithm for the DFS is discovery and finish time. I'm not going to actually tell you why we are adding it. Let me actually just show you how we add it. Then later on in some algorithms, I will show you that why they are going to be very useful, how we can use this discovery and finishing time. So what is this discovery and finish time? I'm going to record when I am visiting the node for the first time and when I am done with visiting all the nodes that I can visit through this node. I don't really care about the actual time. The only thing that we care here is that we wanted to know that, if you consider some steps, if I step by step go over the algorithm and visiting the nodes, I wanted to know the order, which node has been visited before the other node. So these numbers, this discovery and finish time is going to just give me an idea of in which order I have visited the nodes. Let me actually just show you that how we update the algorithm to take care of this discovery and finish time. I'm going to define a global variable which is called time. At each step, whenever you visit something, you just increase the value of the time, and whenever you are done with some node, it's just like in your function call. Whenever you enter a function call, you update the time, you increase it, and whenever you go out of the function call, you update it again, you increase it, right? So this is going to be, the time is going to be updated in the function call, at the beginning of the function call, and at the end of the function call. It's just to record when you start going to a function call and when you finished it. It's exactly the idea of when you discovered the node, when you finished, when you are done with actually checking the node. And what we do is that we record the time somewhere, where we define an array, two arrays actually. We define two arrays, one for discovery, for the start, one for finish. So the start for you is going to be set as time whenever I just enter to the function call, and the finish time is going to be set just before I go out of the function. So you see that I'm updating the order of recording and increasing, just depend on what you are actually doing. Either you put the update before the start and you put it before the finish, or you always put it after recording. So either you just need to, if you change the order of these two statements, you have to change the order of these two as well, just to make sure that you maintain them properly. Always record, then update, record, then update. So this is going to cover and keep track of all the times that you are visiting a node and you are actually coming back from the function call and finish it. Let me execute this over this algorithm. This is going to be nice to see that how the start and visit are going to be set here. So you run the DFS over, let me actually use a different color here. I'm going to keep two variables, two arrays, start and finish. In fact, they are going to actually stored here, so corresponding to 1, 2, 3, 4, 5, 6, 7, 8. This was too big. Okay, at the beginning, remember I initialize time to be 1. This is a global variable, so I'm going to keep time here. You call it over the first node, the starting point, which is 1. In the function call, you record the time for the node that you, and then you update it. Okay, so you record the time, and then you update it. So time will be 2. Then at 1, you visit the node 2, right? You see that, no, I am in 2. What the function calls tells me, it tells me to store the start point and then update the time. I would store the start point, which was 2, right? And the time will be updated. It will be 3. Then you go over the loop, right? At 2, you are going to visit some node. You will visit the node 4, and you call the function call over 4. So the time, you then record, you are in the function call of the 4. You have to record the start for 4. So now the start time for 4 will be updated as, will be recorded as 3. Okay, and you update the time. At 4, you visit another node. You will visit, so let me actually just keep all of these edges of the parent as well. So you are at the function call of 5. You have to record the starting point. The start time is going to be 4 for 5. At 5, and then you update the, before I forget, you update the time to be 5. Okay, so at 5, you visit, the order that we preserved in the previous algorithm was that actually I visit 6 first. So you go to 6. In 6, you need to keep the record the starting time. The starting time is going to be 5, right? You update the starting time, it will be 6. And look at this. So in the loop for 6, the only neighbor was 5. 5 was already visited, right? So you don't call any function call in 6. You will be done with this loop, and then you will record the finish time and update the time. So what would happen is that you record the finish time. So the first node that you store the finish time for, that will be 6. I'm done with visiting 5. When I explored it, the time was 5. When I'm done, the time was 6, because I immediately actually it was nothing actually visited after 6, right? So I'm done with exploring 6. There is no other node that you can go from 6. Then you go back to 5. So you were here, you explored, right? And then you go back to the beginning and check that if there is any other node in any other neighbor of 5 that you can visit. Yes, there is. 3 hasn't been visited, right? So you will visit 3. So you call the function call over 3. So now inside the function call of the 3, you will record the time. So the time, the start time for 3 is going to be 7. Okay, and from 3, and you update actually the time here as well. The time will be 8. At 3, there are 2 other neighbors that you haven't visited, just first visit 7, for example. 7 hasn't been visited, so you check 7, you call the function call over 7. So in the function call of the 7, you record the start time. So the start time for 7 was 8. At 7, there is one neighbor that you haven't visited before. That is going to be 8. So you check that node and you call your DFS over 8. Inside the function call, you will first, sorry, I forgot to actually update the time before we move. So this update has been done in the function call of 7, okay? Then you call the function called the DFS explore method over 8. In 8, you have to store the starting time, which is going to be 9, and update the starting time. Update the variable time. And if you look here, you see that for 8, there is no other neighbor that hasn't been visited before. Okay, so basically this loop will iterate, but it doesn't going to call any other function call. You go to this line. So for 8 as well, you will record the finish time, which the finish time for 8 is going to be 10. No, you can see that I haven't actually marked any finish time for other nodes. Only 8 and 6 has been done. So let me actually show you that the red edges are going to be the edges in the DFS tree. What I am going to show here to you are just the callback. I mean, when you come back from the function calls. From 8, you go back to 7. Just before actually going back to 7, we need to update the time as well. I mean, remember here, after you record the time, you have to update it, just to make sure that you nicely keep the track of the time in finish and start completely distinct numbers. Okay, you go back to the function called 7. In 7, there is no other node that hasn't been visited, right? So we will record the finish time and update the finish time, increase it by 1. And then from 7, you go back to the parent, the one that has called this. So in 3, there is no other node that hasn't been visited. So you record the finish time. So for 3, the finish time is going to be 12. You update the finish time. And from 3, you go back to its parent, the one that has called it. It is going to be node 5, right? So we record the finish time for 5, which is going to be 13. Update the time. And from 5, you can see that from 5, the parent who called it was 4. You go back to the node 4. In 4, you are done. You have to record the finish time. So there is no other node to visit, right? So you record the finish time for 4. This is going to be 14, and you update the time. At 4, you go back to the function call 2. 2 has called the 4, right? In 2, there is no other node that hasn't been visited, so you need to record the time and finish the function call. So the time for 2 is going to be 15, and you update the time. And you go back to, from 2, the function call is going back to the function call of 1. And in 1, there is no other node that hasn't been visited, so you you record the finish time, which is going to be 16. The time will be updated. And then you go back where? Actually, the whole function call will be finished because you called over the explore over the 1. Okay, so this is the result. All the starting and finish time. We record them, we keep them in an array, but to make it actually better to visualize it, we usually put this starting and end time as some label in the graph just to visualize it better. So the starting and end point for 1 is going to be 1 and 16. The starting and ending for 2 is going to be 2 and 15. Start and finish point for 4 is going to be 3 and 14. Start and finish time for 5 is going to be 4 and 13. Start and finish time for 6 is going to be 5 and 6. For 3 it is going to be 7 and 12. For 7 it is going to be 8 and 11. For 8 it is going to be 9 and 10. Okay, something like this. Measure just a start point and finish point. You use it as a some label over the nodes of the DFS tree. This is going to be the result. So there is a very nice property about this start and finish time of the nodes, which is very, in fact, intuitive. If you look at the nodes here, you will see that all these brackets of start finish times for all the nodes, either the brackets are going to be disjoint completely or they are going to be nested. What does this mean? It means that if you think about any two, for example, 2 and the node 2 and the node 3, the bracket for 2 is 2 and 15. The bracket for 3 is going to be 7 and 12. Now you can see that these two brackets, this is inside the bracket for 3 is inside the bracket for 2. Or for example, the bracket of 7 and 2. The bracket of 7 is 9 and 10. The bracket of 2 is 2 and 15. This bracket is exactly completely inside. They are not, they don't have conflict in this way that, for example, some part of it is here, some part of it is outside. Either the bracket is completely inside or completely disjoint. So for example, 6, the bracket for 6 is 5 and 6, right? This bracket time. This is completely disjoint from 3. The bracket of 3 is 7 and 12. This is completely disjoint from the bracket of 7. The bracket of 7 is 9 and 10, right? This is completely disjoint from this. But this is covered by 5. The bracket of 5 is completely inside the bracket of 5, which is going to be 4 and 13. This is completely inside the bracket for 2, which is 2 and 15. Okay, if you take any of the nodes in the DFS tree and you check the starting finish time bracket, either they are covering, one of them is covering the other one, or they are completely disjoint. And what does this mean? If they are covering, one of them is covering the other one, basically it tells you that the one which is broader, the one which is covering the other one, is the ancestor. So now you can see that 2 is the ancestor of 5, this is the ancestor of 6, it is the ancestor of 3, 7, 8. From 2 in your DFS tree, there is a path from 2 to 5, 3, 6, 7, 8, all of them. And if they are disjoint, it means that they are not, there is no relation of descendant ancestor. For example, 6 is not the ancestor or descendant of 3. 6 is not the ancestor or descendant of 7 or 8. And you can see that the bracket for them, the time bracket for them, is completely disjoint. I think this is quite intuitive. This is just based on the way that you call the function calls. The proof is here, but I will leave it for you to read it. So this is actually coming back from the back edges. It is telling you that every edge which is not a part of the DFS tree, is going to be a back edge. It means that it is connecting some descendant to some ancestor. All the nodes which are not a part of, and I think, I mean, when we actually discussed about the back edge, we saw that this is, very, again here, intuitive, that if the edge is not a part of the DFS tree, this is definitely is going to be a back edge. It means that you actually are connecting some descendant to some ancestor. Okay, now I'm going to talk about the properties of the DFS, some nice algorithms that we can solve using DFS. About the BFS, the interesting property of the BFS was that when you run the BFS, the BFS tree will give you the shortest path from the node that you run the BFS over that to all the nodes which are connected to that. So that was the properties of the BFS. We don't have such a property for the DFS tree. DFS tree is not going to give you the shortest path, but it gives me a couple of some other properties that helps me to solve problems like if I'm going to look for a cycle you have a graph, you wanted to see that if there is a cycle, and how can I actually detect that cycle? Or if in your graph you wanted to detect some critical edges or critical nodes. What does actually critical edge or node means that if you remove the edge or if you remove that node, the graph will be disconnected. So look at this, an example of a critical node is something like this, that here I have one critical node, which is going to be this node. It means that if I remove this node, the graph is already connected. But if I remove this node, the graph will be disconnected. An example of a critical edge is going to be something like this, that you have a so in this graph, I have one critical edge. I remove this edge, you see that the graph will be disconnected.